Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. And in this lecture, which is lecture number 64, we will be looking into the parasitic capacitances in nanosheet FETs and extraction of different components and their analytical model, right? So we are looking at a new device structure which has come up as per ITRS, which is known as International Technology Roadmap for Semiconductors. One of the devices which has come up is basically a nanosheet FET. So we will be looking into that, and we'll look at the parasitic components of NSFET. We'll look into its model, and then we will finalize the resultant discussion part in a sense. So let's look at how nanosheet is different from bulk device, right? We have already covered FDSOI for cryo at RF applications. We have done that in our previous lecture. And now we will be looking into nanosheet FETs, and we will be looking at its capacitive model and RF application, including self-heating effects. Now, in the left-hand side, if you look, it's almost like a generic FET device. It's a planar FET device where you have a gate, source, and a drain, and you have a nickel silicide source and drain structure. And then you have also a box layer. It's an FDSOI structure. So you have a box layer of silicon dioxide, buried oxide, below which you will have an epitaxially grown silicon with you. And obviously, these are prone to n number of disorders as well as residual impurities are there, because you will be actually annealing and then doing oxidation, so on and so forth, and there will be many amount of impurities available. Now, this was developed by certain scientists over a period of time. On the right hand side, if you look, is basically a nanosheet. The nanosheet is nothing but where you divide the channel into thin sheets connecting source and drain. So if you look, the structure, three-dimensional structure, this is my source, this is the drain, right? The yellow colored profile which you see here, the yellow colored here, these two, is basically the gate which is surrounding the channel. What are the channels here? If you look very carefully, this and this are the channel. So basically, if you cut it like this, you will see this to be as the gate, right? And there will be channels which will be something like this. And this is the gate here. So this is channel number 1, this is channel number 2, let us say channel number 3, and this is a metal gate, and then there is an oxide layer which is surrounding the channel in this manner. It's actually a FET device, and it's also a MOS structure. Just the fact that now, rather than having a single channel, you have multiple channels available to you, right? And that improves the drain current to a larger extent. And on the left and right hand, so this cross section which I have drawn here, the cross section which I have drawn here is by cutting it from this axis, So if I assume this to be as x bar, so basically cutting through x and bar like this, vertically cutting it, and then after vertically cutting, if you look from this side, right, from this side, then this is the structure which you will see, right? And there will be 3 channels across which the current will flow. The gate is the yellow one which is given here, and the gate is responsible for all sorts of biases for creating an inversion layer in the channel. Now, I will be discussing some papers, and in that paper, research paper, the authors have actually discussed the analytical model to extract the value of the capacitances in the device of a nanosheet structure. They have used what is known as a elliptical integral methodology, elliptical integral method, right? These are only applicable for underlap structures. So this is gate, right? And I have a source here. This is the underlap region which you see, this one, right? You don't have gate overriding it. So basically, the channel potential here is relatively larger as compared to one within the gate itself, right? And that's another thing. Many of the CFET structures have used actually conformal mapping to a larger extent, right? Many of the authors have used conformal mapping for designing the device and using that for the purpose of designing it, right? And that's the reason the authors have used such a design. They have also used the inner fringing capacitances as well as outer fringing capacitances in modeling purposes. And what they are proposing is that the analytical model they have developed is of the order of around 1% error is there, which is quite a small an error between the extracted value and the analytical value. So this is a 3-sheet stacked NSFET, right? So we will be looking at 3-sheet stacked NSFET, And and the way we will be moving forward is we will take up individual capacitances, and then we will add up the overall capacitances in the system. This has been done on a Centaurus platform, which is a Synopsys Centaurus platform, on a TCAD. So this is a TCAD which we are using, and the structure and the dimension is actually shown here. So if you look carefully, this is the structure which they are proposing, and within which we have three stacks actually: one stack, two stack, and three stack, right? So there are three stacks which are available, and it is surrounded by this gate. So knowingly they have actually removed the gate structure to show the gate design, and the gate have been removed, and the structure has been shown here in a much more detailed manner, where if you look at the cross section, the channel is always available. This is the channel length between source and drain, right? And this is the height of the channel which you see, and this is the oxide layer which you see in front of you. And the same thing, if you further cut down, or maybe have a look from this side, like this cutting you are doing, then this is my height of the channel, this is the width of the channel, right? And this is the height of the channel, and this is the oxide layer TOX which you see. And then you will have the width of the device, total width of the device, this thing, right? So the first diagram is cut along AA plane, and the second diagram is cut along BB plane, right? And that's the reason you see both the structures. So looking from the BB plane will make you also understand that the current is flowing into the laptop or into the desktop, wherever you are seeing, or into your mobile, and the source is away from the mobile, and the drain is maybe internally inside the mobile itself, right? Now the silicon doping has been taken to be 10 to the power 15 per centimeter cube, and the oxide stack is, they have used a stack here. Now stack basically means that dual oxide layer stacking is done of silicon dioxide and hafnium oxide, to keep the EOT small as much as possible, and they have calibrated with some experimental data on a platform. With this structure, mixed mode AC simulation runs to obtain the parasitic capacitances. For example, overlap capacitance, gate to drain, and gate to source capacitance. The authors have used knowingly three stacks, possibly because of the reason that the calibration was done using a three stack device itself. Then the experimental data available to the authors from an open source was basically a three stack device. So the calibration was also done using a three stack device in that case. And that's how we can look into the geometry of a three stack nanosheet FET. So let's go to the various parasitic components which are available in this case, various parasitic capacitive components in the nanosheet FET, right? The first one is basically a parallel plate capacitor, as you can see this one, and the capacitance exists between the sidewall of the gate and the source drain region. So if you go back to your previous slide, if you look at this gate, and this is source drain, so it is an extended source drain. So the capacitance between this point and the capacitance between these 2 points is basically my extended source drain region. So the capacitance exists between the sidewall of the gate. So if you have a gate like this, and you have a gate finishes here, your source is here. So from the sidewall to the source, you will have or source, and this side drain, you will have there will be a parallel plate capacitor, right? And the source drain region is composed of epitaxial layers and of course metallic contacts, and the parallel plate capacitance CP will act like a parallel plate capacitor between these two components. So if you look very carefully, this is my CP, as you can see, right? This is my, maybe this is my device channel itself, and these are the source and drain region, and at least let us assume it to be drain. Then CP is basically the parallel plate capacitor which happens between the active region and the source drain region, in a sense, right? So CFGE is basically my fringing capacitance between gate and source drain region, and this arises due to electrical field which is present. So what is happening primarily is that there is a fringing field which is happening between the channel and the gate side. There is a fringing field which is happening. This fringing field extends beyond the direct overlap. So as you can see, the reason it is referred to as in the extension, source drain extension region, and that results in some capacitance which is referred to as CF. So this is your CP, this is your CFGE which you see in this case, right? We will go one by one and explain to you individual one of them. Now then CF pi I have written it. So inner fringing field will be there, and there will be also an outer fringing field will be happening. So there are 4 directions in which it can go, basically top to top, front to front, and so on and so forth. You see, I have a channel here, I have a channel here, I have a drain to source here, right? So there can be a top to top capacitance here, bottom to bottom capacitance here, right? So therefore this takes care of top to top and C bottom also. So this is basically a three-dimensional structure, understand. So one will be like this, which is C top to top, this is C bottom to bottom, this is C back to back, and this is C front to front, right? So in all the four directions there will be capacitance, and these will be all external capacitance which we will see, outer fringing. So the previous one was inner fringing, this one will be more of an outer fringing capacitance is available to you. And these outer fringing capacitances can be found out, and they do contribute to the total parasitic capacitance of the active layer of the device. However, the value of these will depend upon the structural parameter. For example, what is the height of the sheet, or what is the height of the active layer of the device, what is the width of the active layer of the device, and that will ensure that the value of CTT, CFF, CBB and CBOT is basically extracted a priori even before when you start the methodology or extracting the parasitic capacitances. Then you will also have the junction capacitances between the channel and the source drain extension region due to the junction formed. So we have done see this, we have done this, we have looked into this, we have looked into this and this. So this is the junction capacitances, right, between the channel and the region. Obviously, see, if that region is basically storing charge, right? So this, if that region is storing charge over a period of time, then that will result in what is known as a junction capacitance. So CJU is basically my junction capacitance in that case. Now, if you remember when we were discussing CF pi in the previous region, it consists of CTT top to top, front to front, back to back, and bottom to bottom. What the paper says is that among all of them, the bottom CBOT will dominate the CF pi region, right? And if you look carefully here, within which you also have good contribution of CP, which is CP is what? CP is your parasitic capacitances, which is happening parallel plate capacitance. This is CP. This is the maximum which you get, but within all the four CF pi, the bottom one dominates over the other one. So C bottom is approximately 13% of the total cap value, and others are just 3% or 5% and so on and so forth. The maximum contribution is of course from the parallel plate capacitor, which is happening, which is approximately 45% is such. Now C bottom is this one. C bottom is bottom one. So let me just show you why bottom one is there. This is the C bottom, bottom to bottom, and if you look very carefully, C bottom to bottom goes via BDI. BDI is basically known as the dielectric isolation, right? This is basically the dielectric isolation which you give. So bottom dielectric isolation we say, which BDI is referred to as a BDI is bottom dielectric isolation. And this is meant to generate such that your off currents are reduced and you don't allow a fourth channel to form beyond the 3 channel, because if you remove BDI, then there is a probability that the source and drain region might be connected through the silicon layer, and just like a bulk MOSFET will form a channel, because you don't want the calibration to fail, and second thing is you don't want the power dissipation to go high. So what you do is that you do a bottom dielectric isolation you generate, which is basically a silicon dioxide when you do. In fact, when you do that, then because of high dielectric constant of BDI, the capacitance increases, and that is the reason it is approximately 10% larger than other forms of CF pi. And this increases the parasitic capacitance to a larger extent. Then you have a large effective field penetration. Electric field from the bottom fringing field downward can spread more into the BDI. If you remember, the effective area increases, right? And therefore, your effective capacitance increases. If the now let's look at the closer vertical spacing. Now, if the vertical spacing between the gate and the source drain bottom is very small, the fringing field is very strong because you're bringing them very close to each other. When the fringing field is very strong, you end up having a very large amount of charge being accumulated there, and that's the reason C dominates CF pi, because of the very strong electric field. So three reasons why is it so. One is because of BDI, which is typically a high K material. So if you remember, your C is epsilon naught or K times your by Tox, A by Tox, right? epsilon k by Tox. Now, if the k value is relatively high, even for a moderate value of A and Tox, your C value will be also very high. That happens with the BDI because it's made of a high K dielectric, right? And second thing is, since they are very close to each other, the parasitic paths are also very large, making the capacitance also very large. So with this idea, let's come to the capacitive model which is with us. And what you see on the right hand side is basically the authors have given the electric field modeling of the NSFET nanosheet FET and a type of parasitic capacitance. As I told you, CP will form via the vertical parallel plates, and more spatial extension is there, less the value of the capacitance will be there. And the junction capacitance models are typically complicated because they consist of both horizontal as well as vertical as well as horizontal field due to gate bias and doping differences. And the model which they have proposed helps the reader to understand that how does device geometry and material they contribute to the total parasitic capacitance. As you can see on the right hand side, the yellow one is basically gate to source drain parallel plate. Then you use junction between the channel and the capacitance, and this is your outer fringing field. You see, this one is the outer fringing field. This is the bottom, this is the side one, this is the top to top, and that will be bottom to bottom on the back side of the device itself. So this is the basic sort of a capacitive model which has been extracted here. Now let's deep dive into each of the parasitic cap and see how we can move ahead to do the parallel plate capacitance model. Now, if you remember, CP was the parallel plate capacitance because of the field between the spacer and the gate itself, and we know that it is epsilon naught into epsilon r into A upon D, where D is the distance between the side walls and A is the overlap area between the side walls, and epsilon r is the relative permittivity of the spacer material. Now, the overlap area is not just a simple rectangle because the device has complex geometry and different regions contribute to the different value. If you look at this device here, the effective width of the channel you should see is W. The actual width is given by this one here, right? And these are the various fringing field and external values of the. So HAP is basically the epi layer height which you see, right? And then HM is the metal layer height which you see, and then front gate which you see in the top extension region which you see is FE. So the authors have divided the whole region into various areas, and they have tried to calculate the various areas, and then when they have done that, the overlap area is added between A1 plus A2 plus A3. And obviously the A1 is the most easiest one because this is HM multiplied by W device. So you see, this is a rectangular operation, HM W device, where HM is the height of the A1 region and W device is basically my width of the device, and therefore this represents a vertical sidewall overlap area between the metal contact of source and the gate. Let's look at area number A2, which is this one and this one here. If you look here, it is W into width of the device multiplied by HAP comes out to be this one. I'm not going to details of how they calculated, but this is how it is done, where N is the number of stacks or a number of active nanosheets which you are doing. Now, this means that the area here is basically directly contributing to the value of CP, and we are excluding the fringing field areas in such case. A3 is written again in this fashion, and it is given by this expression at this particular point. Now, the junction, so if you add A1, A2 and A3, you get the total area. When you put the total area back into the other parameters, you will get the junction, you will get the CP value here, the parasitic capacitance. As I discussed with you earlier also, that the basic model of a junction capacitance is written as a parallel plate capacitor, and its value CJU is given by this value, which is epsilon naught R into epsilon naught into W is the width, H is the height, W into H gives you the area, divided by LJ is the junction length which you see, the effective length of the fringing electric field, right? And it is basically an electrostatic effective length which you see, that will give you the value of CJU, right? CJU is the junction capacitances. Now, various people have actually done empirical modeling of LJ. The LJ is weakly depending on the value of L, the junction length actually. So, I assume that my initial junction length is 0.5 nanometer, and as I change the value of W and L, the overall junction length, the effective junction length, goes on changing. As you can see, as you increase the value of W and L, the L value will go on increasing in a non-linear fashion, right? And this helps me to capture the effect of scaling effects on the capacitance of a device. Now let's come to the doping dependence. We know that your source drain, there will be a doping, and there will be doping concentrations there. Now if you modify the doping in the source drain region, it implies that my junction length will also vary in a sense, and therefore my CJU will vary. That's what is written here, right? That the depletion region width at the junction will vary, and the extent of the electrical field coupling will also vary. And they are modeled by this equation which is written here. And what we are assuming is that R is a parameter which is linked to the source drain doping strength. Higher the doping, obviously larger will be the R value in such a scenario. R is not resistance, please understand. So higher the doping, larger will be the R, and therefore higher will be the cap, right? Now at high doping, the device shifts towards overlap architecture, increasing further coupling. Why? Because at high doping, when you make the doping concentration high, the R value increases. That implies that your CJU will increase. You can understand from the other concept also that it is basically epsilon into A by T. So your T basically reduces, and therefore your capacitance goes on increasing to a larger extent. And that increases the coupling much further than what is expected in this case, right? And that's the reason it is doping dependent quantity. Now, Now we will look into junction capacitances versus channel length. So what we do is we plot CJU. The authors have plotted CJU versus the channel length, right? For various channel lengths, which we find out for different, and they have been done for different widths. So when the width was varied from 20 to 50 with a step size of 10 nanometer, and the observation was that the CJU value increases with W. However, its dependence on channel length is relatively weaker, right? And with W, it of course increases because the area goes on increasing as you make the line. The solid lines are the model predicted this thing, and the dotted line are your model parameters which you see. Similarly, if you plot capacitance versus source drain doping concentration, then CJU gives you a model parameter which is going on varying, and it goes on increasing as you make the doping concentration higher and higher, which we have just now studied, and this is a numerical derivation for that. And the FGE value, which is basically the gate to extension fringing field capacitance, which is the red square here, right, is also increases. So as the doping increases, both the capacitances rise, and that's reason why, because the depletion width decreases and electric lines are coupled much more better in the fringing field area. Now if you look at the dashed line which you see, this is the model line which you see. The R value is the sort of a regression analysis, and you can find out the value. And the solid black line is the one which shows the model trend of the equation. They have not found a very large trend in this design, but nonetheless, physically it looks almost the same in both the cases. If we look at the capacitance versus sheet height, as the sheet height therefore increases, the capacitance increases, because larger vertical electric field cross section means larger overlap area, which effectively means more electric lines will terminate, and that will result in a higher capacitance. So the excellent match is there for various values of technology for different technology nodes which you see here. Similarly, so these are CJU, CFGE versus width. The overall trend is that with increasing width, the capacitance starts to increase further and further, right? And when it goes on increasing further and further, the value of the parasitic capacitances goes on increasing, and that's primarily because of better coupling, stronger coupling between the devices. And this is good agreement across the number of sheets. So if you vary the number of sheets, the structure still remains the same, and you are able to have a linear profiling of the values of the capacitances. And they show very good extreme scalability of the model from narrow sheets to wide sheets. If you look at the spacer thickness, so spacer is basically the region between the underlap, basically the region between the source drain and the gate itself. Now, as you make the spacer length go on increasing, the general trend of CP is to decrease, right? And that is expected also, because you are shifting both the arms larger. Your T oxide falls down, your effective T falls down. rises, and therefore your capacitance starts to fall down for a fixed value of height, width, and length. And the same trend is almost for all other cases, and then that's the reason you see this capacitance versus spacer thickness available to us. So this figure therefore combines all the parasitic on the right hand side. This is C total plotting with respect to H, W, L, and spacer length. And overall, as you can see, that for almost all the cases except the SPR spacer, there is always an increase in the value of the capacitances with respect to H, W, and L, right? And this is expected, as I discussed here. However, with increasing value of the spacer length, there is a decrement because of the fact that there is always a fall in the value because the effective electric field reduces in such a scenario. So this is the general capacitance formula, which for a two parallel plate inclined in an arbitrary angle phi, a conformal mapping technique is available by which you can find the value of C phi with respect, if you know the value of small k and capital K, this thing, where small k is the modulus depending on geometry and capital K is the complete electrical integral of the first kind. And the modulus k from the geometry is found by this methodology, and from C phi we get this. The error is typically very small, which is 3 into 10 to the power minus 6 in this case. The relative error in parasitic capacitances, if you look typically the pillbox diagram here, is maximum for C pi, right? CF pi shows you a maximum percentage error, right? And for other cases, the relatively small error. So even for the maximum spacer length, CF pi, it is only about 3.1%, approximately 3%, which is less than 4% across all the components, and therefore it shows to me that the capacitance model extracted by the authors are very accurate, and they are used in compact modeling for TCAT simulations, right? This is for an n number of sheets, and what their authors have done is that they have increased the number of sheets from 1 to 3, and they are trying to find out the effective value of CJU, CF pi, CFGE, and CP, right? And what we have seen is that with increase in the value of n, there is no linear increase in the value. There is a non-linear increase in the value of all the capacitances. So let me recapitulate what we learned in this lecture. And what we learned was primarily we looked into a nanosheet FET, right? How is it different from a bulk device? We looked into that. And we looked into the various capacitive models within the nanosheet FET, which was proposed by the authors of the paper, which I have referred in this presentation slide. And these capacitive models are primarily again subdivided into various different types of model which are physically validated. They are also compared with analytical model, and good match is found between the two. And finally, we looked into if we vary the number of sheet, how does the overall capacitance varies with the structural parameters available to us. So this gives me a holistic idea about the various elements which are there in a nanosheet FET. In our subsequent lectures, we will see how it works on a cryogenic scale, right? Okay, thanks a lot for your patient hearing. Till we meet next time, goodbye.